Okay, welcome to this talk on quantum cryptography with classical communication. I'm Tony. This is joint work with Alexandru Gheorghiu and Alexandru Poremba. And what I'll talk about is a kind of transformation that we can do on quantum cryptographic protocols to make them, in a certain sense, less quantum. So I'll begin by explaining what exactly this dequantization transformation, if you want to call it that, what this achieves, and also what we pay for it and when you should and shouldn't apply it. Then I'll explain the main technical tool that underlies this transformation, which is a protocol for what we call parallel remote state preparation. And finally, I'll end on some open questions. Okay, so to explain this dequantization transformation, we'll start from what I'll call the original protocol. And this you should just think of as some quantum cryptographic protocol that someone else has come up with and that we would now like to dequantize. And we would like to dequantize it in as generic a way as possible. But for this transformation to be possible, we do need some amount of structure on this original protocol. So what structure does the original protocol need to have? We have two parties, as is very common, Alice and Bob. And the first message in this original protocol has to be Alice just sending random BB84 states, n of them, to Bob. Okay, so these are the BB84 states, 0, 1, plus or minus. We can also write them a little more compactly like this. So this is now a tensor product of these states. And if theta here, this I'll call the basis choice, if this is 0, then depending on what this VI is, we get the state 0 and 1. And if theta is 1, then we get the states plus and minus. So theta is the basis, and VI I'll call the value of the BB84 state. And just intuitively, why is sending random BB84 states a useful first step in many quantum cryptographic protocols? Roughly, the idea is that if Alice sends these states, Alice knows precisely which states she sent, right? She knows these bases and values. But Bob, on the other hand, he just receives some quantum states, right? He doesn't know the basis, so he can't measure to find out the value. Really, he doesn't know anything about theta I and VI, but he still does have these states. So he's in possession of these states that depend on theta I and VI without actually knowing what these values are. And this asymmetry of knowledge, where Alice knows what these values are and Bob doesn't, but nonetheless has states that depend on them, this is usually what is leveraged in the protocol that follows. Now, for our purposes, we don't really care about the protocol that follows, as long as this protocol is entirely classical. So we do require that the remainder of the interaction here is just classical messages back and forth between Alice and Bob. And we also need that for Alice to execute this protocol, once she's sent these BB84 states, she only needs to do classical computation to compute her next response to Bob. Okay, so this kind of protocol we can kind of split up into a quantum and a classical part. So pictorially, the quantum part is this. It consists of Alice sending random BB84 states to Bob. And then Bob may have to be quantum throughout the protocol. And indeed, for this dequantization transformation to be interesting, he will usually have to be quantum for at least a part of the protocol. So this means that for an honest Bob to succeed in this protocol, at least succeed in a computationally efficient way, it may be the case that Bob will have to keep some coherent quantum state around, and to answer Alice's questions later on in the protocol, measure a part of this quantum state, and then maybe apply some unitary, measure a different part, and so on. Okay, so Bob may be quantum throughout. But crucially, Alice, once she sent her BB84 states, her quantum career is kind of over. She only does classical computation now, and she only sends classical messages. So this entire communication here and her actions are purely classical, as I said. Okay, so this is the original protocol. Now, what would we want the dequantized protocol to look like? So really what we want to dequantize here is the quantum communication. So we want to replace this first quantum message from Alice to Bob by a classical protocol. And if we do this, then pictorially, this looks like this. So now Alice is purely classical, as is the communication between them. But Bob, nonetheless, may have to still be quantum in order to be able to succeed in this protocol with computationally efficient operations. Okay. Now, this classical protocol here will really kind of have to replicate sending these BB84 states. So, we still want a situation where Alice knows these theta I's and VI's, and this classical protocol will somehow depend on them, but the protocol will have to depend on them in such a way that Bob doesn't find out what theta I and VI are, but nonetheless is able to prepare BB84 states if he behaves honestly. This second part of the protocol here, this we just want to copy over unchanged. So this is what makes this transformation generic, is we don't care what's going on here. We just copy it over, and all that we really ever touch in the protocol is this first message here. All right. Now, one thing I want to stress, just language-wise, is I call this a dequantized protocol, but really, what we dequantize is the communication. It's not purely classical. Bob still has to remain quantum. So what this talk is about is going from the left to the right. Okay, so before I explain how this transformation works in more detail, I just want to give you some examples of protocols that follow the structure, mainly to convince you that this is an interesting class of protocols that is worthwhile studying. So the most famous example of a protocol that follows this structure is the BB84 quantum key distribution protocol, which is also where these states here derive their name from. And in this protocol, Alice and Bob want to generate some shared key. And the way they do this is that Alice sends over random BB84 states to Bob, who measures them in a random basis. And then they do some classical communication to correct errors and do something called privacy amplification and so on. Right? This is a very old protocol, one of the very first quantum cryptographic protocols, but there are also much more modern ideas of protocols that still follow the structure. So one is something called unclonable encryption, introduced by Broadbent and Lord. And what this achieves is it gives Alice a way to take a classical message and encrypt it into a quantum state, a quantum ciphertext, in such a way that Bob can't clone this quantum ciphertext. So Bob can't create two copies of the quantum ciphertext that, once he receives the keys, could then individually be decrypted. There's also a notion called quantum copy protection, which is quite similar to unclonable encryption, except that instead of Alice encrypting a message, Alice has some kind of simple program that she wants to encrypt into a quantum state in such a way that Bob can execute the program but not create sort of pirated copies of the program. Okay. There are also certain notions of delegated quantum computation, which also have protocols in this structure. Okay, and there are potentially many more that I haven't listed here. It's not meant to be exhaustive. So you don't have to know what these protocols do in detail. My main point here is that there exist protocols that do have the structure, and it might be interesting to study their dequantized versions. Okay, so now let me tell you a little bit about what we gain and what we lose when we do this dequantization transformation. So the obvious thing that we gain is that in the original protocol, Alice needs quantum capabilities in order to be able to prepare these random BB84 states and send them over. But in the dequantized protocol, Alice is purely classical. And likewise, this original protocol requires a quantum channel connecting Alice and Bob. But the dequantized protocol only requires classical communication. So in principle, you could just run it over the internet if you like. So this is the good part. Now onto the disadvantages, like what do we pay for this classical communication? So the first thing that we pay is that this original protocol here may be information theoretically secure. It doesn't have to be. I mean, this depends on what's going on down here, but it may be information theoretically secure. On the other hand, the dequantized protocol will always rely on a computational assumption, and in particular, it will rely on the assumption that learning with errors is hard quantumly. This is kind of a standard post-quantum crypto assumption. Right, and the reason is that this first classical protocol here that we use to replace the BB84 states, this already depends on LWE. So no matter what's going on down here, the whole thing will only be secure or sound as long as we believe in the quantum hardness of LWE. Another thing that we lose is that this original protocol can have negligible soundness error. And this roughly means that a cheating party will only pass in the protocol with negligible probability. Again, it doesn't have to, right? This again depends on which protocol we're looking at, but it might have negligible soundness error. But when we dequantize it, we'll always lose this property and only get inverse polynomial soundness error. And this, similar to this computational assumption, is because this first classical protocol already has inverse polynomial soundness error, and then the soundness errors just get added up, so you will never go below inverse poly. Right, and the final thing that we may lose, again, this is something that depends on the specifics of the original protocol, is that it may be the case that in this original protocol, Bob only needs to implement a certain sort of easier subset of quantum operations instead of doing full quantum computation. Whereas in this dequantized protocol, in general, this requires more quantum capabilities from Bob, and naturally, we also do lose something in parameters. So one thing I want to make very clear is that certainly at this stage of development, this is not meant as a tool for making quantum cryptography sort of more NISQ ready and easier to implement with noisy near-term devices. We're interested in this because we kind of want to know in a generic way, what quantum cryptographic protocols really require quantum communication and what primitives can we just as well implement with classical communication. But this is not about making any protocol NISQ ready. Okay. That said, if you do care about implementing this maybe at some later point in the future, the 2 points here that I think can be improved quite a lot compared to what we have now is, firstly, I do think it should be possible to preserve negligible sinus error with some sort of more sophisticated techniques. And secondly, it's certainly possible to reduce the overhead that Bob incurs in this dequantized protocol. We just haven't put any emphasis into optimizing this. Now, the one thing that you won't be able to get rid of as a disadvantage is going from information theoretic to computational security. So this is really something that's very much baked into this notion of dequantization, that it does rely on a computational assumption. So with this in mind, in particular, this point about having a computational assumption, let's go back to the examples from the previous slide and look at what would happen if we run these protocols through this dequantization transformation. Like, what would we get out? So if we start from BB84, what does BB84 achieve? It's a way of doing key distribution. So if we run this through the dequantization transformation, we get a protocol that has classical communication and achieves key distribution and is secure as long as we believe that LWE is quantumly hard. But this is kind of pointless, right? If this is your goal, you should just use public key crypto based on LWE. Like, there's really no point in taking BB84 and going through this whole business just to get another classical computationally sound key distribution protocol. So while in principle you could apply this dequantization transformation, there's really no point, like you shouldn't. On the other hand, these other 3 primitives here, they are for functionalities that just don't make sense in a purely classical world. So as a result, if we apply this dequantization transformation, yes, some of them do have information theoretic security to begin with, and of course we lose that, but we still get something out that would be impossible if Bob here were classical, right? So for example, if we look at quantum copy protection, it just doesn't make sense in a purely classical world to try to take a program and encode it into a string and hope that somehow no one can copy that string. Like, you can copy any string, right? There's no point in this. So even though we do rely on a computational assumption on this side, we still get something that doesn't make sense in purely classical crypto. So as a general rule, this dequantization transformation is useful or interesting for quantum protocols that achieve primitives which are impossible in purely classical crypto. Or in other words, for primitives which, even in this dequantized setting, still require Bob to remain quantum. Okay, so now I want to move on to explaining how this dequantization transformation works in a little bit more detail. And this relies on a primitive that we call classically instructed parallel remote state preparation of BB84 states, or just parallel RSP for short. So to understand what this parallel RSP protocol needs to achieve, let's go back to the very first slide. So this is what we want from our dequantization transformation, right? We want to take the sending of the random BB84 states and replace it by a classical protocol, which I've now labeled parallel RSP, that achieves much the same thing, right? We still want it to depend on bases and values, and we still want that Bob is left wondering what these bases and values are, despite being able to prepare the corresponding BB84 states. So we can write down these requirements and say that this parallel RSP protocol that we're looking for is some interactive protocol between classical Alice and quantum Bob, such that at the end of the interaction, if Alice accepts Bob in the protocol, then Alice knows some random bits theta I and vi, the bases and values of the BB84 states. Bob is in possession of these corresponding BB84 states. And crucially, Bob does not know any additional information about these values theta I and vi. Okay, so this reflects the fact that Bob should be sort of left wondering what these values are, except for having the information about them that is sort of contained in his BB84 states, but that he can't just use to find out what they are. Okay, so this is what we want. We can state this a little bit more formally by saying that the joint state at the end of the protocol should be close to this. So let me decipher this for you. This first thing here is just some uniform expectation over bases and values, reflecting the fact that we're interested in preparing uniformly random BB84 states. Then the second part here is just classical information, right? This is a diagonal, just a projector. This belongs to Alice, and this stores her information about theta I and VI. The second quantum system here, these are Bob's BB84 states. And then finally, Bob may have some auxiliary quantum state that he prepared as part of the protocol, right? We can't prevent this. Bob can always prepare some extra quantum state, but that's fine, right? He's allowed to do that. Okay, so these are the uniformly random bases and values choices. This is Alice's classical information. These are Bob's BB84 states, and this is some quantum state. Now, what's crucial, though, is that this additional quantum state should be independent of theta I and VI, because remember that we wanted that Bob doesn't have any information about theta I and VI except for what's contained in these states. So consequently, whatever additional state he prepares, it's fine, as long as it doesn't tell him anything about theta I and VI. Right? And this, of course, can only hold under the assumption that Bob can't break LOE. Now, this is still like a little bit too good to be true, so we need to make some modifications. And one modification is that we can't prove that this state is close to this state, so the actual state is close to this state. We can only prove that it's computationally indistinguishable from this state. And the reason for this is as follows. So, what has to happen in this protocol? Somehow Alice has to give Bob enough information about theta I and VI so that he can prepare this quantum state, but not enough information so that he actually finds out what theta I and VI are. So intuitively, this is not quite true, but you can, for intuition, imagine that Alice sends over like an encrypted version of theta I and VI that somehow allow Bob to prepare these states. But then this auxiliary state can depend on these encrypted versions of theta I and VI. Right? All that we require then is that these encryptions don't actually tell Bob any useful information about what theta I and VI are. So in other words, while the true auxiliary state may depend on these values information theoretically, from Bob's point of view, they don't tell him anything useful. And as a result, they're computationally indistinguishable from a state that is independent and therefore doesn't contain any information at all about theta I and VI. Right, so this is how this computational indistinguishability comes about. The second caveat is that this can only hold up to an isometry on Bob's part of the state. So the second two registers here, or second last registers. And this is because an isometry on Bob's part of the state just corresponds to a change of bases in Bob's part of the state. We can't control what bases Bob chooses for his operations. But this is totally fine because also in the original protocol where you send actual BB84 states, Bob could always just collect these BB84 states and then apply some change of bases on them. And this would obviously not break any security. Okay, so this isometry here is really not an issue. One thing that I want to stress is that we really need to prove like a tensor product structure on Bob's space here. And this is because these original protocols that I've been talking about, their security proofs usually start by saying, without loss of generality, assume that Bob first receives these NBB84 states from Alice and then does something to them. And in that original setting, this is indeed without loss of generality because Alice sends these BB84 states one by one. So therefore they arrive in a tensor product, and we can assume that Bob just waits for all of them at the start. But this is not the case here. There's no Alice sending single qubits to enforce a tensor product structure. But if we just want to drop in this RSP protocol into the existing proof, we still need to have a tensor product structure because the proof assumes this, right? So instead, we have to somehow cryptographically enforce this tensor product structure here. And this is really the technically challenging part because this also involves showing that Bob's Hilbert space has a certain minimum dimension so that it's even able to contain these BB84 states. Right, so this also serves as a kind of proof of quantum space in some notion, if you like. All right, so I won't really have time to say anything more meaningful about the proof of this theorem, like the soundness proof of this protocol. So what I'll do instead is just mention some related work and then sort of vaguely hint at how we might be able to prove soundness of this parallel protocol. So this whole business of dequantizing quantum cryptographic protocols really got started with Mahadev's celebrated verification protocol. And in our language of dequantizing things, you can view this as a way to dequantize so-called receive and measure protocols, where instead of Alice sending random BB84 states to Bob, Alice receives qubits from Bob and then measures them either in the computational or Hadamard basis at random. So it's kind of the flipped around version from the kinds of protocols that we've been looking at. And Mahader's work gives a very nice way of dequantizing such protocols using these post-quantum crypto tricks. And this turns out to be sufficient for classical verification of quantum computation. Now, the first work that really considered these prepare and send type protocols that I've been talking about, where Alice sends random BB84 states to Bob, is this work of Gheorghiu and Vidic. And what they construct is a single qubit RSP protocol. So precisely what I've been talking about, but just for a single qubit without any tensor product structure. And this turns out to be sufficient for dequantizing blind delegated quantum computation. But this is only possible because there's this prior work here which showed that a certain composable notion of single qubit RSP is sufficient for that. But in general, of course, if you just do single qubit RSP, you can't dequantize generic protocols because you lack this tensor product structure on n qubits. Now, there's also been some work that we've done on something that we call computational self-testing, which is a kind of variant of remote state preparation, which has also been extended to magic states. I won't say too much about it. And I also want to mention concurrent work by Fu Wang and Zhao, who give a parallel computational self-testing protocol of EPR states, so kind of a parallelized version of this, which is quite similar to our parallel RSP protocol on a technical level. Okay, so this is work on sort of generic dequantizations or generic computational protocols with classical communication. There's also been work on what I'd call application-specific dequantizations. So for these cryptographic primitives, what you can do is you can look at that specific primitive and come up with a protocol that only has classical communication using these same kinds of post-quantum crypto ideas. So compared to our work, this doesn't have any generic transformation. So you need to do extra work for each primitive that you want to dequantize, and in many cases, quite non-trivial work. But what you get for your extra work is that you are able to preserve negligible signless error. So this is definitely an advantage of this application-specific approach. Now, in the context of this previous work, what you can view as our main technical contribution is proving a kind of parallel rigidity of this GV19 protocol. So proving that if you do this protocol in parallel, then indeed the prover also has, in a very strong sense, to behave in parallel and prepare the corresponding qubits in parallel as a tensor product. The proof of this is, on a technical level, quite similar to these parallel self-testing proofs from the non-local games literature, but then with some like crypto tricks sprinkled in. Right, so let me end on some open questions. Firstly, and kind of obviously, you can apply this transformation now to additional protocols. In our paper, we've applied it to a good number of protocols, but there are more that you could dequantize using these ideas. Another thing that is definitely possible is to reduce the overhead on Bob's side. As I've mentioned, we've put no effort into doing this, and it definitely can be improved. But I think the most interesting question is to preserve this negligible signless error. And for this, it seems like you can't use our definition of remote state preparation. This is, in a certain sense, too strong, and it seems impossible to get this with negligible signless error. So one option would be to have some weaker definition of RSP. I'm not quite sure what this definition should be. There's one suggestion by Jiayu Zhang in work on linear time verification, which looks like a good candidate. And with this weaker definition of RSP, it might be possible to have something that preserves negligible signless error and is nonetheless sufficient to dequantize existing quantum crypto protocols. A sort of vaguer idea would be to prove some sort of unclonability property directly from post-quantum crypto. The motivation here would be that currently what we do is we have this RSP protocol to prepare BB84 states, but then the protocols that we plug these BB84 states into, they don't really care about the BB84 states themselves. They just care about the fact that BB84 states have this unclonability property. So it seems like it ought to be possible somehow to circumvent this strong RSP statement, just go directly from the post-quantum crypto assumption to some unclonability statement, and this way also preserve negligible signless error. Okay, so I'll end here, just put up the references briefly in case you want to look any of them up, and I thank you for your attention.